2024 A-Level Combined Mathematics Paper 1 Part A question number 1. This is the induction question. The question says, using the principle of mathematical induction, prove that 7 to the power of n minus 1 is divisible by 6 for all n elements of the positive integers. So basically, for the set of positive integers, which is the set that goes 1, 2, 3, 4, 5 and so on, for every single n in that set, we need to make sure that 7 to the power of n minus 1 is a multiple of 6. And to be a multiple of 6, of course, you just need to be 6 times some integer. For example, if you take 18, the reason 18 is a multiple of 6 is because it can be written as 6 times an integer, which is 3. If you take 24, 24 is a multiple of 6 because it can be written as 6 times an integer, which is 4, and so on. So similarly, we need to show that if you take any positive integer n, which is in the set 1, 2, 3, 4, 5 and so on, and you take 7 to that power minus 1, the answer you get is 6 times an integer. Now in any induction question, we know the first thing that you have to do is to establish the base case. For this set, which is the set of positive integers with that goes 1, 2, 3, 4, 5 and so on, we can see that the best base case would be the very first element in that set, which is the element 1. So therefore, the first thing we're going to do is to try this thing, try for n equals 1. Now for n equals 1, all we can do is to substitute n equals 1 into this thing and see what we get. So considering that, if we substitute, we're going to get 7 to the power of n, which is 7 to the power of 1, minus 1, which is 7 minus 1, which is 6. But I'm not going to stop here. Instead, to make sure it is clearly visible that the number we get of 7 to the power of n minus 1 is divisible by 6, I'm going to write this as 6 times 1. So now it is clear that our answer is 6 times some integer, which means it is true that it is divisible for n equals 1, and therefore we can say, therefore, true for n equals 1. So for n equals 1, we can see 7 to the power of n minus 1 is divisible by 6. Now given this, the next step in mathematical induction would be to assume for some element of the set that we're trying to prove for, and then given that, we would want to try for the next element. So in this case, I'm going to say assume true for, and I'm going to say some element n equals, let's say, p, where p is an element of the set that we want to prove for, which in this case is the set of positive integers. So we're going to say p element of the set of positive integers, so we can say is it plus, and this is what we're going to assume for. So we're going to assume that it is true for n equals p. Now what we're assuming true for n equals p is that 7 to the power of n minus 1 is divisible by 6. So we're going to assume that 7 to the power of p minus 1 is divisible by 6. Now, if any number is divisible by 6, as I said, it means that the number can be written as 6 times some integer. Now, due to this, if 7 to the power of p minus 1 is divisible by 6, we can say definitely that, therefore, we can say something like, therefore, 7 to the power of p minus 1 is equal to 6 times some integer, and for our purposes, we are going to use the symbol, let's say, k. So we can say 7 to the power of p minus 1 must be equal to 6 times k, where k is some element of the positive integers. If for n equals p, where p is some element of the positive integers, 7 to the power of p minus 1 is divisible by 6, then 7 to the power of p minus 1 must be equal to 6 times k for some integer k. Now given this, the very next thing we want to do is to test for the next value after n equals p. For this case, we can see, since we're testing for the positive integers and we're doing n equals p, we want to do the next value, which is going to be n equals p plus 1. So now we're going to try for n equals p plus 1, which is the next value. Now considering the next value, what we have to try is to take this expression here and substitute n equals p plus 1 and see what we get. So considering that, we have 7 to the power of n minus 1, which means we're going to get 7 to the power of p plus 1 minus 1. Now considering this expression, what I want to do is to convert this expression into a form that contains either 7 to the power of p minus 1 or 7 to the power of p, because then I can substitute from this expression that I assumed up here and simplify down to something that I can use. So considering this expression, we can see the 7 has a power of p plus 1. And from what we know by index rules, if you have a power of a plus b, it is that base raised to the first power times that base raised to the second power. So therefore, this 7 to the power of p plus 1 minus 1 is equal to 7 to the power of p times 7 to the power of 1 minus 1. Now considering this thing, we can see what we have is 7 times 7 to the power of p times minus 1. So we have 7 to the power of p, which I'm going to put a bracket for a placeholder here, minus 1. Now considering 7 to the power of p, we can see in this expression 7 to the power of p could have been written as 6 times k plus 1. If we took this minus 1 to the other side, we can see 7 to the power of p is equal to 6k plus 1. Now if I had called this equation number 1, I could say from equation number 1, we can substitute 7 to the power of p over here for 6 times k plus 1 and say that this is going to be equal to 7 times 6k plus 1 minus 1. And now we can see if we expand this 7, we are going to get 7 times 6k, which is 42k, and we're going to have 7 times 1, which is going to be plus 7, and then a minus 1, which we can see can be simplified to 42k plus 6. And we can see here there is a factor of 6 in this thing right here and this thing right here. If you factorize that out, we can see we have 6 times, and on the inside we have from this thing 7 times k, and from this thing plus 1. So therefore our answer is 6 times 7k plus 1. Now considering the expression that we have here, we have 6 times a number, and this number is 7 times k, which is an integer, plus 1, which is another integer, and therefore 7k plus 1 itself is another integer. Now due to this, we can say since the number we get is 6 times another integer, then the overall thing is definitely a multiple of 6. And therefore, if this thing right here, 6 times 7k plus 1 is a multiple of 6, then the original number, which is 7 to the power of p plus 1 minus 1, is also a multiple of 6. So we can say therefore 7 to the power of p plus 1 minus 1 is a multiple of 6, and for a reason why, we can say it is equal to 6 times 7k plus 1, and 7k plus 1 is an element of the positive integer. So we can say it's a multiple of 6 since 7k plus 1 is an element of the positive integers, and that is sufficient ruling, sufficient information, sufficient logic for us to say that 7 to the power of p plus 1 minus 1 is a multiple of 6, since we can clearly see here we have 6 times an integer. Now given this, we can see we have proven that 7 to the power of p plus 1, or the next value, is in fact a multiple of 6. Now given this, since we've proven for n equals 1, if we take p to be equal to n equals 1, we can see we are going to be proving for n equals p plus 1, or n equals 1 plus 1, or n equals 2, and then when we try n equals 2 for p, we can see we're going to get p plus 1, which is 3, and therefore if we start with the base case of n equals 1, we're going to get n equals 2, n equals 3, n equals 4, and so on. So therefore with this, we have completed our induction proof. All we have to do now is to say therefore true for n equals p plus 1, and with that we can finally write the sentence that we write for every single induction proof here, and we can say since the above was proven true for the base case, true for, and in this case the base case is n equals 1, so we'll say true, proven true for n equals 1, and when assumed true for a given value, when assumed true for, and in this case we assumed it true for n equals p, so we can say assume true for n equals p, and when we assumed it true, we found it true for n equals p plus 1, so we can say when assumed true for n equals p was found true for n equals p plus 1, And with that, our statement for that part is done. And now all you have to say is, hence, by the principle of mathematical induction, the above is true for all relevant n, for all relevant n, which in this case we were asked to prove for n element of the positive integers, and we can see with this n equals 1, n equals 2, n equals 3, and so on, we have done exactly that. So we can say the above is true for all n element of the positive integers, and that is the end of this question. Now finally, let's take a look at the marks order for this question. So at the start, when you try for the base case, which is the n equals 1 case, and you substitute 7 to the power of 1 minus 1, which is 7 minus 1, which is 6, and if you write it as 6 times 1, and you say therefore true for n equals 1, you get 5 marks for that. Now after this, when you assume true for n equals p, where p is some element of the positive integers, such that 7 to the power of p minus 1 is divisible by 6, for this statement, you get 5 marks. After this, when you formalize the statement by saying 7 to the power of p minus 1 is going to be equal to 6 times k, when you write that part, you get another 5 marks. So when you write this part where you say it is divisible, you will get 5 marks. And when you define what it means to be divisible as this right here, you get another 5 marks. Now after this, when you try for n equals p plus 1 and you simplify like this by substituting, and you get to the form 6 times an integer which is 7k plus 1, and you write that since 7k plus 1 is an element of the positive integers, and we have 6 times that being equal to 7 to the power of p plus 1 minus 1, we can say that 7 to the power of p plus 1 minus 1 is a multiple of 6. And then when you say therefore true for n equals p plus 1, all of that work, all of this stuff right here gets you 5 marks. And then finally, when you write this sentence, which basically doesn't change in between questions for every single year, it's basically the same exact thing, you just need to change the values slightly. But other than that, if you write this sentence correctly, where you make the correct conclusion by stating the base case, the assumption, and the final conclusion, and you say hence by mathematical induction the above is true for the relevant n, which in this case is n element of positive integers, when you write this statement, you get another 5 marks for a total of 25 marks for this question. So that's going to be all for this video. I hope you enjoyed. If you have any feedback, post them in comments down below. Thank you for watching, and goodbye.